Good day, everyone. So today we're going to go over section 13.4, and this should be a fairly quick section here because all we're doing is running a hypothesis test comparing two population means. And um, so it's the same five steps as before. It's just that we're applying it to uh, comparing two population means. All right, so here's our example, samples of Penn State students, and this was actually done. Were taken in their sex and pulse rates were recorded. A researcher wanted to investigate whether there's a difference in mean pulse rates between Penn State men and women. So we'll make, since the problem stated women first, we'll just make all Penn State women population number one and all Penn State men population number two. Could you have switched those around? Absolutely. You could have made either one population 2. Here, we'll make the women the first one, men the second. 35 Penn State women were sampled, and their pulse rates and their mean pulse rate was 76.9 with a standard deviation of 11.6 beats per minute. 57 men were sampled. Of course, they were Penn State students. All right, and mean was 70.42, standard deviation 9.95. All right, test 5% significance level. So there, we know that we're running a hypothesis test, whether there's a significant difference in the mean pulse rates. All right, and um, so there is N1, X bar 1, S1, and so we can see all that from our problem here. It's at 35 and 76.9, 11.6, okay, N1, X bar 1, S1. Then we have the information for the men 57, 70.42, and 9.95. All right. All right. So state the hypotheses. And so with hypothesis testing, when you're doing a two-sample t-test, um, the null hypothesis, you have your option, but they're pretty much saying the same thing. All right. You can write it as mu1 is equal to mu2. So meaning there's no difference. That's what the null is saying. No effect. That's why we call the null the null. All right, null meaning empty or zero in mathematics, and so there's no effect. Whereas we have h sub 0, mu1 minus mu2 is equal to 0. That's another way that you could write it. Now, most people like to write it this way, all right, and that's fine. However, there's a benefit for seeing it like this at least, and you'll see why later on. All right, that's why I wrote it. I rewrote it as mu1 minus mu2. All right. The alternative, you have your choice. We'll have to you have to read closely into the problem to figure out what to put. So either we can put greater than, less than, or not equal to mu1 versus mu2. And again, you could write it like that as mu1 minus mu2. Up to you. Conditions. We need the sampling distribution for x bar 1 to be a t-distribution, and we need the sampling distribution for x bar 2 to be a t-distribution, so that when we subtract the two, that sampling distribution will also be a t-distribution. So in other words, we need either n1 to be greater than or equal to 30 for the central limit theorem to apply, or we need x1 to be normal. If we have either one, that means the sampling distribution of x bar 1 is a t-distribution. And we need exactly the same thing for the second one, right? So that the sampling distribution of x bar 2 is a t-distribution. Well, as long as you have either this or that, and you either have this or that, that means both of these distributions are a t-distribution. So when you do the subtraction between the two, it will also be a t-distribution. That's basically what I said in words up here. Okay. All right, and then we also need independent random samples. All right, we need those samples to be independent of one another. Remember, they can't be dependent. That means if they're dependent, we would be running a paired t-test. Test stat. Here's the test stat. Notice it's just sort of rewriting the confidence interval a little bit. Okay, the only thing that we have to really talk about is this part right here. What is this? Well, okay, I got a question for you. When we were just testing one population mean in the formula, we had mu sub 0. Well, where did mu sub 0 come from? That came from the null, right? Came from the null. So where do you think mu1 minus mu2 with the little sub-zero is coming from? Well, the null hypothesis, right? And what's in the null? Now, this is the reason why I rewrote mu1 is equal to mu2 as what? mu1 minus mu2. What's the value in the null hypothesis? It's a big fat 0. So this value right here, all right, turns into, it's kind of silly, but it turns into 0, okay? You might be asking, well, why do we do that? Well, it is possible that if you got into another stats course that you don't necessarily have to put always 0 there. You might want to test if mu1 minus mu2 is, there's a difference of, say, 4 or a difference of a minus 10, okay? I mean, that's totally up to you. And so whatever number that you're putting in there for the difference for the null hypothesis, technically you would put that here, okay? And you would run the test then. But for the most part, okay, you just usually want to see if there's a significant difference. And if you just want to see if there's a significant difference, well, that number is always going to be 0. And for this class, it'll be 0. All right, so that's what the numerator turns into. And so actually calculating the test stat isn't too bad. All right, p-value. That'll come from the t-distribution because the test statistic is t, right? So the test stat is t, so we're going to go to the t-distribution. Now, reminder that the degrees of freedom is pretty ugly for when you're comparing two population means, all right? And so we're going to use StatCrunch to help us figure out then the p-value. Conclusion. All right. So same as always, right? P-value is less than alpha, the significance level will reject. It's greater than alpha, do not reject. All right. And remember what that means is that both the null and the alternative are still very plausible. Okay, just about every possible scenario is still plausible at that point. All right. All right, so let's go back to our problem. And I think we can run through this one. So state the null and the alternative hypotheses. There's the null. There's the alternative. Now, why did I put not equal to? Because over here I said test at the 5% significance level whether there is a significant difference, right? So we didn't have any kind of inkling if the mean pulse rate was going to be greater for men or women. If we did, maybe we would go ahead and put a greater than sign or whatever. But we didn't know that. Okay, we didn't have any idea of that, and so we just wanted to see if there was a difference. All right, and difference suggesting not equal to. So remember what we're doing. We are testing both greater than and less than at exactly the same time. Two-tailed test. All right, verify conditions. Nothing was mentioned regarding the normality of either sampling distribution. All right, but certainly the essential limit theorems are applying here. That means the sampling distribution of x bar 1 minus x bar 2 is a t-distribution. I would certainly hope that in reading through this problem, you would see that the samples were independently done. They're not dependent samples; that they're independent samples. Okay. This was a real problem that I copied out of another textbook, and I copied it word for word. Hopefully they did it randomly, okay? So maybe I should have added that in there, but certainly needed to be randomly done. Calculate a test stat. All right, so there's our test stat. Remember, we're going to throw in 0 into here. So I did all the math for us, okay, and that made a test stat. That's a fairly significant t, 2.743. So that means our x bar 1 minus x bar 2 was 2.743. Standard error is above the value in the null. And the null, remember, was saying what? mu1 was equal to mu2. All right. And so it looked like the pulse rate for the women, all right, if I had to guess that, because I said that this is a pretty high for a T, with any kind of reasonable degrees of freedom, that notice that uh, the sample mean for the females was higher than the males. All right, so uh, that's why we got a positive number here. All right, that's the only reason why. All right, moving on. Calculate the p-value. All right, so I went ahead and put this into StatCrunch, all this information. All right, and I got a p-value of 0.0079. So that seems pretty significant, right? Uh, we would go ahead and then compare that to alpha, and alpha was 0.05, so we're going to reject the null. So this is what I want you to pay attention to. All right, that's what I want you to pay attention to, is that this statement is okay, but it's not good enough. All right, so it's okay, but it's not good enough. So you could say that there's simply a difference in the mean pulse rates between the Penn State women and men at the 5% significance level. So you could say that, but to me, that's not good enough. All right, because remember, we were testing not equal to. And so if you reject the null when the alternative has not equal to, that means either the test picked up that mu1 was either greater than mu2, all right, or mu1 was less than mu2, all right. It was one of the two. And just to say that there's a difference when we can actually figure out which one it was based upon doing nothing else other than running the hypothesis test, all right, we should state that, all right. So, well, let's think about this. Can you think this one through? Which one was it picking up on? Remember, the females was the first population, and the males was the second population. What do you think? Well, look at the remember I kind of pointed this out before, is that the mean pulse rate for the women was 76.9, for men was 70.42. And so clearly, if there's a difference between the two, it's not going to say that that mu for the females was less than the mu for the males, all right, when the sample means were the opposite, all right. So uh, here, clearly, it's telling us that the female pulse rate is greater than the male pulse rate. The other thing that you could think through was that um, the test stat was positive. The x bar 1 minus x bar 2, that was positive. However you want to, there's a couple of things that could have told you that. All right, that tells us that mu1 is greater than mu2. All right, to be honest with you, that's the only example I really have for you. Now, there is more here, all right, but with regards to a two-sample t-test, there's really nothing else really to it. I think you would just sort of be bored if I went through another example. After going through confidence intervals and things like that, I, you know, I and all the explaining with hypothesis testing, to go through another example, I think would be not very beneficial. So I'm just going to kind of move on. If what I could do is that I have other courses, that I have other problems, I could put those lectures out there too, just in case you may want to see more examples. But I think this usually would probably suffice. All right, so let's let's go ahead and see how confidence intervals and this hypothesis testing would relate to one another. So since we declared that mu1 was greater than mu2, what should we expect from the confidence interval? Would we expect two positives, two negatives, or a negative positive? Think about it. Well, we should expect the entire confidence interval to be entirely what? Entirely positive. Because we're saying that mu1 is greater than mu2, all right? And so, so if we ran through the confidence interval, which I did here through the computer, I came up with 1.76 for the lower bound, the upper bound 11.2. All right, so notice the entire confidence interval is positive. So if mu1 was less than mu2, what would we expect the entire confidence interval to be then? It would be entirely negative, right? And if we could not tell a significant difference, what would we expect in that situation? We would expect the confidence interval to be the lower bound to be negative, the upper bound to be positive, okay? And that's what I wrote down here, all right, on this slide. So if the entire so this is the results of the confidence interval, all right, if it was entirely negative. We would reject the null if the alternative had less than 0, or for that matter, not equal to 0. If the confidence interval was entirely positive, then we would reject the null if the alternative had greater than 0 or not equal to 0 in that situation. And the do not reject situation, meaning we had inconclusive results, we would expect the negative positive. All right, and there we go. Because remember that confidence interval has a 0 in it. All right, and so if the null has a 0 in it, well, that's basically saying that's a possibility. Okay, all right, but we're not saying to accept it. So notice what I put here. I keep on saying the same thing over and over and over again, just to make sure that you get it. So notice that the value in the null is 0. It is a possibility in the confidence interval, but we cannot accept it because the confidence interval is also telling us that a negative is possible along with a positive value for the difference. So all possible situations are still very plausible at this point. All right, last thing that I want to talk about with regards to comparing to population means is what's called effect size. Effect size, and so this is something that a lot of researchers would go ahead and go through these calculations, okay, to have even a better understanding of the difference between the two populations. So effect size is simply a way of quantifying the size of the difference between two groups. This allows us to analyze further the results we get from hypothesis testing or confidence intervals when comparing two population means. So I saw a program where it claims that teenagers should actually go to school later in the day, and early elementary schools like kindergarteners and first graders, okay, they should go earlier because how kids generally sleep. So if, I don't know if you have little brothers or sisters or what have you, and you ever notice how little kids they're up early, you know, mom, dad, wake up, wake up, wake up, right? And they do that early. And so um, so in generally speaking, what happens with teenagers, they tend to what? Sleep in, right? And so but usually the school systems have it exactly the opposite, where the teenagers actually go to school first, and then the kindergartners and the first graders, second, they actually go later. Okay, so let's say that we ran an experiment with teenagers as to when they best learn, morning or afternoon. If we randomly selected groups and there was no overlap, all students in the afternoon group, uh, let's pretend this happened. Okay. So if we randomly selected groups and there was no overlap, all students in the afternoon group did better than uh, uh, even the best student in the morning group. There's no mystery how to interpret. We know that all of the one group was greater than the other one. Okay, but that's not very reasonable to think that way. Okay, so we go ahead and have to sort of think of it like this. So let's say that this is the afternoon group in blue. This is the morning group in red. All right. Those are the two distributions. They're not sampling. These are populations here. Okay. This is the distributions for X1 and X2, if you will. All right. So notice that there is overlap. We do have students over here, right, that overlap with these students over here. But generally speaking, this group is a little bit further over to the right and do better in learning. Okay, so the higher the number, the better the learning. Okay, well, notice that these are both, let's see, this one in blue is centered at, it looks like 70, and this one in red is at 60. All right. So let's say that we took a look at these guys. All right. So here, this one is still centered at 70. This one is still centered at 60. But what happened to the standard deviations? The standard deviations is getting a little bit smaller here versus over here. So smaller, but they're centered at exactly the same spot. Okay. And so what's going to happen here is the effect size will be higher between these two versus these two. All right. And I'll show you how to calculate the effect size. So different way. Now there are different ways of calculating the effect size. So I'm just going to show you one way. And if if another class or researchers say, hey, we calculated the effect size, or we need to, just note that there's different ways. But I'm going to show you probably the most straightforward way. All right. So often when comparing to population means, we actually kind of standardize. Now, what does standardization mean again? That means to go ahead and calculate Z, right? And so you can think of that as the effect size, that it's a Z, all right? And to calculate it, remember, we don't know what mu1 is, we don't know what mu2 is, and so we'll just use the sample stuff. And so it's x bar 1 minus x bar 2 divided by some sort of standard deviation. Now, the standard deviation is supposed to be from the population from which the different treatment groups were taken. However, in practice, this is rarely ever known. Remember, we hardly ever know what the population, once you combine the two groups together, what the population standard deviation is going to be. So that number either must be estimated from the standard deviation of the control group, all right, or remember how we talked about the pooled T and we had a pooled standard deviation? Well, you can also do that. Okay, so like I said, there is different ways, and just depending on the scenario, all right, you'll choose the right one then for to put into for the standard deviation. Now, I'm not going to have you do that in this class, all right? I'm just saying that in practice, you would have to figure out which one to put in there. Should we put in the standard deviation from the control group, or do a pooled T, or whatever? Okay. So that's so here's our two populations again. Okay. Oh, the effect size. So here, the standard deviation from the control group, which we'll say is that group right there, turned out to be 10. So notice here that it was centered at 60, and then you go over 1, 2, 3. We're pretty much at the edge there, right? 1, 2, 3. We're pretty much at the edge, all right? So that would make the standard deviation 10. And so the effect size would be 1, because we have x bar 1 at 70, right? The other one at 60. We divide by the standard deviation. How about with this guy? Well, here S actually turns out to be 5. All right, it's remember we said it was smaller. So here's 60, right? And then we go over 1 standard deviation, right? And then we go over 2 standard deviations, and then 3 standard deviations. We're pretty much there, right? 1, 2, 3. And so notice it's just 5. And so the effect size over here is 2, all right? So let's interpret then the effect size for these two groups. Now, in looking at textbooks, there's a whole bunch of different ways of interpreting effect size, but the most common way for statisticians is that the effect size now is a z-score, all right? So for example 1, the effect size was 1, all right? What this suggests then is that that the student with an average score, okay? So in the group that was a little bit larger, this suggests that the student with an average score in the let's see, what was the color in the blue group. Okay, so what we're saying is that a student that was sitting right here with the blue group, average, okay, is 1 standard deviation above the average student in the control group. Makes sense? Therefore, the average person in the experimental group scored better than 84.13% of all those that were in the control group. Wow. Let's look. So if you were average in this group, okay, notice how far over you are in the red, okay, which is that second population there. All right. And so notice it's all of that. Okay, that's quite a bit. And if you think of this as a z-score of 1, well, how much data is before z of 1? Well, let's get out of here for a second. Okay, let's go over to our standard normal table right here, and let's go to a z-score of 1. Let's check it out right here, 84.13. All right, 84.13%. Okay, so that's where we're getting that. And so let's get back in the presentation here. What about this one? This one had an effect size of 2. Let's interpret that one. All right. This suggests that the student with an average score in the one that was further to the right, okay, is 2 standard deviations above the average score in the control group. Therefore, the average person in the experimental group scored better than 97.72% of all those were in the control group. Wow, that's pretty significant. Okay, it really sheds some light into stuff. So if you go back here, go to that graph. So here's the graph again. Let me get my pen out. Here's the average person from control group, and notice that how much of the students are below just the average person over here. So that's 2 standard deviations. So notice that's a lot, right? And so again, if you went to the standard normal and looked up a z-score of 2, all right, that's telling you where I'm getting this number right here, this 97.72%, all right? So effect size. So you see that a lot of times in people's research, all right? So now you have a better idea of how to interpret that, okay, if you run into it. All right, thank you for your time.